Hello everyone. Our topic is dining philosopher problem. We use Go language to research this problem. The most important reason we use Go is that Go has coroutine, which is friendly and powerful to concurrent programming. And Go has built-in channel so that threads can easily communicate with each other without depending on some framework. Besides, Go is lightweight and easy to learn. Well, let me introduce dining philosopher problem. There are 5 philosophers sitting around a dining table, and some food on the table center. Between every 2 adjacent philosophers, there is a fork. That is to say, 5 forks in total. If someone wants to eat, he or she must take forks on his or her both sides, so that the neighbor cannot eat at the same time. So we are trying to find solutions to help these 5 philosophers eating without deadlock and starving. Well, it's straightforward to find the first solution. In this solution, a hungry philosopher waits to take his first fork, and then he waits until his right fork available and take it. Thus, the philosopher have both forks and can eat. After eating, the philosopher put back both forks and in its turn. Well, it's obvious that this solution is not good, for it will raise deadlock. Consider this situation. All the philosophers hold their left forks and wait for right forks, and all of them cannot move anymore. They got deadlocked.
Okay, so this is the code for natural solution. At first, we will introduce some keywords. The first one is goal. Goal starts a goal routine, which is a lightweight thread, we can say, in goal implementation. Goal routine will run in the background and run concurrently. The second keyword, sync wait group, which we define here, is like a counter of number of goal routine we created. It decreased by 1. We can use done here to decrease the counter when one goal routine finishes. And in the main function here, it will wait and block the execution here until the value wg here back to 0, which means all goal routine we create are finished. So here we create 5 forks as 5 mutual exclusion blocks. That means lock 1 fork correspond to take 1 fork here. And release a fork means that unlock a mutual exclusion. And we create 5 goal routine as 5 philosophers. They will follow the same behavior, like taking the fork, left fork, right fork, and eat the food, and release the right fork and left fork. Left fork and right fork. So in these 2 steps here, they might be blocked at one of those execution, since the fork is already locked by other philosophers. Now let's run the code. Now we can see that each philosopher will take the fork one by one and cause a deadlock.
In order to avoid deadlock, we improve the first solution and get a second one. In this solution, all forks have different number, For simplicity, we assume that philosophers are labeled from 0 to 4, and forks are also labeled from 0 to 4. A philosopher and his left fork have the same number. If a philosopher wants to eat, he will compare the number of forks in both sides and wait and take for the fork with smaller number. If he has this fork, he will wait and take the other fork. After he has both fork, he will eat and put back both fork in this time. In this situation, no deadlock will occur. Consider this situation. Philosopher 0 and 4 contain both fork 0. Philosopher 1, 2, 3 hold fork 1, 2, 3 respectively. In this case, philosopher 3 can also take fork 4 and eat.
This is the code, and it's pretty similar to the first one. The only difference is that the last philosopher will take the right fork first, then take the left fork. And we can see there's no deadlock when run the code.
The third solution introduces an arbitrator called waiter to determine if philosophers can eat. In the solution, if a philosopher wants to eat, he will send a request to the waiter. And the waiter will check if both forks are available and allow philosopher to eat. Otherwise, it will reject the eating request. On receiving a permission to eat, the philosopher can pick forks directly and begin eating. After eating, the philosopher put back forks and notice the waiter that eating is done. The waiter will check the availability of forks and proceeds other requests.
And this is the code of waiter solution. Inside the solution, waiter and philosophers use channel to communicate. Channel is the other concurrency primitive in Go. We can simply use make here to create a channel with specific type and use a left arrow, which is here, to send the message to the channel or receive a message from the channel. The final keyword is select, which will choose one case to execute if they receive the message. At the beginning, we create those channels, then run a waiter go routine to handle requests from philosophers. In the waiter function, waiter will traverse all philosophers who are still sitting at the table in this for loop. If waiter get one message from one philosopher and request to eat, waiter will check if both folks are occupied by others, then accept or reject this request, then send message back to philosopher. Then the philosopher go routine is pretty simple, as constantly just request to eat, then wait for reply, eat, and send message say, oh, okay, I'm done, to waiter.
The fourth solution is called Chandy and Misra because it's introduced by them. In this solution, every philosopher have a number, and each fork can either be dirty or clean. Initially, all forks are dirty, and each fork are given to a philosopher who need it and have the lowest number. When a philosopher wants to eat, he must check if he has both fork. If he doesn't, he will send a request to another philosopher who holds the fork. On receive a request, the philosopher must hand out the fork if it's dirty, or keep it if the fork is clean. When fork is transferred to another philosopher, the fork is washed clean. And if a fork is used by a philosopher, the fork becomes dirty.
And this is the code of Chandy-Misra solution. We also use channel to make sure every philosopher can communicate with the philosophers in his left and right. Inside the philosophers function, philosopher will first handle the request from his left and right neighbor. For example, his left neighbor will send a message for requesting a fork, and he will decide either give the fork to the neighbor since he is finished eating, or refuse to request because he haven't eaten yet since the fork is clean. In addition, he might receive a fork from neighbor or receive a refuse. After processing those messages, a philosopher will want to eat and check if there are two forks on his left and right. Otherwise, send a message to his neighbor just like what he just received before. If he grabs both forks, he'll start eating as usual and make the fork dirty, and loop through again until he leaves the table. And this is pretty much everything, and thanks for watching.